So before we go into the nitty-gritty details of the timers and the states and transitions and all that stuff for TCP, let's just take a high-level look at an introduction to TCP. Stuff that definitely, if you're a CCNA candidate, you should know this stuff. So let's start with that. So let's start a little bit with the history of it. It's very old. It was developed by Stanford University back in the 1970s. And what this was developed for was, this was developed way back before the internet as we know it even existed. You know, way back in these days, the United States Defense Department was creating a network. It was called the DARPA network. It stood for the United States Defense Advanced Research Projects Agency Network. There's a mouthful. So the idea was, they were thinking, okay, well, right now we have, universities and these centers of knowledge that have their mainframes and all their stored information. But what happens if that stuff gets bombed, right? And some war or something gets blown up? It would be nice if all these devices were interconnected so that people could still get to knowledge, they could still get to computers and mainframes, even if one particular path is blown off the map. We want to interconnect all of these things. And so that was the original sort of idea behind DARPA, the Defense Research Project. And so they originally created a protocol which is no longer in existence called the Network Control Protocol, or NCP. So NCP was the precursor to TCP IP. But basically, because of some limitations about NCP, they decided to develop TCP IP, which is kind of interesting, is that originally TCP IP were bundled together into the exact same protocol. It was actually called TCP, but it wasn't the Transmission Control Protocol as we know it today. What that acronym stood for originally was the Internet Transmission Control Program. Internet Transmission Control Program, and it was IP and TCP all together in one specification. But after they wrote that, they realized, well, wait a second. The whole idea behind the OSI model is to have a layered approach so that one layer is not dependent upon another layer. And they thought, well, with the way we've written it right now, if somebody wants to use IP, they have to use TCP. They have to use the reliable nature of it. And these scientists and stuff, they realized, well, there might be some people out there who develop an application that they want their own application to have reliability. They'll build reliability into like layer 7 or something, and they don't really need it as part of TCP IP. So we'll break them apart and we'll have them separate. And then of course they developed UDP for those people who didn't really want reliability and all this other stuff at layer 4. So IP was the protocol suite and ARPANET was the network infrastructure, and then just stuff grew like gangbusters after that. So the original first formalized RFC for this Internet Transmission Control Program, the whole thing was RFC 675. Probably not much reason to read that anymore since it's been separated and a lot of changes have happened, but if you like kind of trivia, that's RFC 675 was that original RFC of the Transmission Control Program. And then TCP itself, when it was separated and made into its own protocol, RFC 793 was the original RFC for that, for the original TCP. And there have been many, many RFCs since then which have modified and added on to the original implementation of TCP. So, what makes TCP different from UDP? Definitely something you want to be able to answer at any level of a certification exam. Well, UDP is connectionless, meaning that when UDP takes some data and slaps a UDP header on the front of it, sends it down to the internet protocol, at that point, UDP forgets all about it, right? UDP says, I don't even know if the destination exists out there. I don't care. My job is simply to slap a header onto this thing with a source and destination port number. That's really all I'm doing, is adding port numbers to this. Send it down to IP and then it's gone. I don't even care to remember it at that point. So connectionless. Also, one thing about UDP is that UDP is really designed for small, discrete blocks of data. So that's what it says here. It's designed to receive small, discrete messages from upper layer protocols. So let's say, for example, that I have an upper layer protocol that when it's creating a socket with UDP. So, within the whole CPU structure and how applications link into other applications, there's an application that says, oh, okay, I'm going to link into UDP, and I'm just going to start sending a constant stream of bytes, just a long stream of bytes. UDP doesn't really know how to deal with that. It doesn't know how to say, okay, when do I stop and package this stuff together into a UDP datagram? It doesn't really have good mechanisms to answer that question. So that's why UDP is really expecting small discrete blocks or chunks of data to come down from the application for the application to say, okay, here you are, here's 20 bytes. Here you are, here's 100 bytes, just little blocks of data. TCP, on the other hand, connection-oriented. So before TCP can even transmit your data, it has to do a whole bunch of stuff. It has to verify that the other end actually exists and is listening and is waiting to receive your data. That's number one. Then it has to exchange all sorts of parameters. Okay, let's agree on some stuff here so our communication goes smoothly. And so after all of that is exchanged, then the data can be packaged into what's called a segment and sent down. But even more than that, TCP has these reliability mechanisms where it makes sure that the data actually got there, and we'll talk all about the details of that. Another big difference of TCP is that it can work with any format of data, including a constant stream of bytes. So TCP has this method of, as data is coming down, the application that's sending it to TCP, that application is going to be storing it in some sort of internal memory buffer somewhere that your CPU has access to. Now remember, first of all, I'm going to do a little disclaimer here. I am not a hardware engineer or a software engineer. I don't know the nitty-gritty structure and details of about how central processing units work and how they grant sockets and memory allocation stuff, but this is what I've gained from my research. My understanding, and some of the live stream can correct me if I'm wrong, is that when an application has data to send, the CPU will say, okay, application, whatever it is, email, web browsing, whatever, I'm going to give you this little piece of memory here called a buffer. And so when you have something to send, put your bytes into that buffer. And then the CPU will say, okay, application, it's your turn. I'm doing all sorts of stuff. The CPU is doing like millions or billions of things per second. So in a tiny slice of time, tiny millisecond, the CPU will say, okay, email, your turn. Do you have anything you want to put in this buffer? And the application will say, yes, I do. And it'll say, bump, 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 bump. There go the bytes stored in this buffer. And now the CPU will say, okay, who do you want to let know that you put that stuff in there? And the application will say, I want to inform TCP of this. So the application will say, or the CPU will say, okay, you're done. Now for the next tiny little time slot of time, I'm going to invoke the TCP process. And they'll say, hey, TCP, that application has just generated what's called a send call. He's just generated a send call saying, TCP, there's some data waiting for you in this buffer. And here's where it starts, here's where it ends. And so now for a few more milliseconds or microseconds of time, TCP can go to that buffer and collect it all and start building some segments out of it. So what does that have to do with this whole stream-oriented nature? So what can happen is when the CPU says, hey, application, do you have anything for me? The application can say, yes, and he starts sending a stream of data filling up these buffers. And eventually, the CPU says, okay, you're done for now. Okay, so stop filling up the buffers. I need to talk to somebody else. And so it can go to TCP. And so basically from our perspective as human beings, this application can just be sending a constant stream of data into these buffers, filling up these buffers with bytes. And every once in a while, TCP will look at that buffer and say, okay, let me take what's in there and make a segment out of it. Or sometimes what TCP might say is, okay, right now, while I have permission, I'm going to go into that buffer, take the bytes I see, and collect them as part of a segment. And then a few microseconds from now, when I'm given permission again, I'll go back into that buffer. If there's more stuff in there, I'll pull it out and add it to my existing bytes. So it might take several processes for TCP to go into the buffer where TCP finally says, okay, I've gathered enough now. I can put that in a segment and send it on its way. So that's why TCP, it doesn't really care about if something came down as a discrete block or if something's coming down as just a stream of bytes. It just looks in this buffer, takes what's out of there, and then TCP itself has a decision to make. Do I stop right now, create the segment, and send it? Or do I wait for the next time and pull some more stuff out of there and make my segment a little bit bigger and then decide to send it. And we'll talk as we go along here a little bit more about some of the details as to how it makes the answer to that question. Do I send the segment now, or do I make it bigger and then send it? We'll talk a little bit about that. So what is meant by connection-oriented? We've talked a little bit about this. TCP verifies the existence of a peer prior to data exchange. So it actually sets up what's called a three-way handshake. We're going to go through that. And the three-way handshake, part of its purpose is to say, hey, server out there, do you exist? Can you let me know that you're actually there? And then during that handshake, they negotiate some parameters used to control data exchange. For example, when talking to the server, maybe the server says, yep, I'm here. And then I tell the server, okay, hey server, when you're sending stuff to me, send me no more than 12,000 bytes at a time, and then I'll acknowledge you. Or send me 8,000 bytes at a time, and then I'll acknowledge you. So they'll tell each other stuff like that, how much they can each hold on to at one time. When a single segment's being created, how big can it be? What's the outer boundaries of that? So all of that will be set up in exchange at the very beginning during this handshake. Now the handshake is done, TCP can start going. And it can exchange data reliably using these sequence numbers, flow control, and retransmission. So TCP says, okay, when I send something to you, I need an acknowledgement back. And as part of that whole thing, maybe when I first talked to you, let's say you and I are TCP hosts. Maybe when we first did this handshake, I said, okay, as you're sending segments to me, I don't really care how many you send to me, but the total size of all of them, send me no more than 12,000 bytes. If you send me 12,000 bytes, and maybe that's in 3 segments, maybe that's in 5 segments, I don't really care. But if you send me 12,000 bytes and I have not yet sent an acknowledgement back to you, pause. That's called flow control. It says, hold on, just give me a chance to process all this stuff. And then when I send you an acknowledgement back, you can keep going. And during this whole back and forth, maybe I'll say, hey, I'm starting to get a little busy here. Other people are talking to me, not just you. And so I know I initially told you that you could send me up to 12,000 bytes at a time, but I can't really handle that anymore. So now I want you to reduce that and make sure you send me no more than 5,000 bytes at a time. So that's another part of flow control, where as this communication is going back and forth, both sides can tell each other, hey, I'm free, send me more stuff. Or, hey, I'm getting a little bogged down, slow down. That's all part of TCP as well. And then, of course, there's retransmissions. Things can happen in a network, right? If two devices who are talking TCP probably are not on the same wire. They're probably not in the same VLAN. And so because they're separated by who knows how many routers and switches, anything could happen in the middle. There could be congestion, there could be data corruption, and so TCP has mechanisms built in to handle that. How does TCP know when something's been lost, and what does it do about it? We'll talk about that as well, but it does have the answers to those questions. And then lastly, TCP can gracefully inform a peer about the need to close a connection. It doesn't always do this. I mean, for example, once again, let's say that I'm a client and you're a server and we're both, doing a TCP connection, and all of a sudden on my laptop, I yank out my Ethernet cable or I shut down my Wi-Fi adapter. Well, if I did that, I didn't give TCP any opportunity to tell you anything. So you're not going to know for a while that I'm gone because I wasn't able to gracefully shut it down. But that doesn't usually happen. Usually you don't rip out the cable or shut down your Wi-Fi NIC. So if you shut down your web browser or you close out of your email, one of the things that happens in the background is that the application, once again, because remember the application and TCP are talking to each other by way of the CPU like being the interpreter saying, okay, you go, you go, you go, you go. Well, as part of that, the application will say, hey, TCP, I'm done. I don't need you anymore. And so TCP will then say, okay, hey, remote server, I don't need you anymore. Let's finish this conversation. And they'll actually send messages back and forth to gracefully close the conversation. So that's also possible. Now here is the TCP header. I'm not going to get into all these right now, but the main thing I wanted to point out by showing you this is because TCP has all these reliability mechanisms built into it, it has a fairly large header. It's got a lot of different fields in here. As a matter of fact, if we're not talking about any options or any padding, just the standard TCP header by itself is 20 bytes long. So now imagine this for a second. There's some programs like, think about Telnet, right? So you're telnetted to something, a router or switch. Well, the way Telnet works is that the moment you type a character, like let's say E or Y or N, Telnet tells TCP, send that right away. Because Telnet says, hey, I don't want you to buffer this stuff. I don't want you to buffer like 25 characters because I might be sending a break signal or something that has to be going right now. So some applications like Telnet that utilize TCP, the actual data it's transmitting might only be like 1 or 2 bytes, but you got these 20 bytes of overhead in front of it because that's what TCP needs to do all of its reliability and everything. So that can be a downside of TCP, is that yes, you have all this reliability, but there's a lot of overhead involved in order to achieve all this reliability. And I just point out here in this slide that a lot of the reliability of TCP actually comes from these code bits, and we're going to talk about the code bits and what they're used for as we go along here.